Average rate of change. Functions are rules, okay? They give us outputs when we supply them with inputs. It says very often we want to know how fast the outputs are changing compared to a change in the input values. Okay, so how fast, or how slow for that matter, they're changing, the outputs are changing compared to the inputs. So this is referred to as the average rate of change of a function. And you're going to see that this is going to sound real familiar, average rate of change. So our first example says Max and his younger sister, Evie, are having a race in the backyard. Max gives his sister a head start. That's some key information. And they run for 20 seconds. That's another key piece. The distance they are along the race in feet is given below, with Max's distance given by the function m of t and Evie's distance given by the function e of t. So when we look at the graph here, we have distance in feet along the y-axis, and we've got it marked out in increments of 10, so then in between are 5s. And then down on the x-axis, we have time, t, in seconds. Max is, his path is here, m of t, and Evie's is here, e of t. It says, how do you interpret? Okay, so that word interpret means find the meaning with the context of this problem. The fact that m of t equals 30. So that's our t, that's our time, and 30 is our distance, okay, in feet. So this means that after 12 seconds, Max has run 30 feet. Okay, or he's 30 feet from the starting line, however you want to think about that. So let's illustrate that on the graph. So 12 right there, 30. Okay? It says if both runners start at t equals 0, time at 0, okay, how much of a head start does Max give his little sister? So here's our t of 0 right here in the corner, and this is Max, and this is Evie. So how much of a head start did he give her? You can see this distance in between. He says, so for Max, m of 0 is 0. But for Evie, whoops, I got to change that to an e. Her e of 0 is different. Okay, times 0. Her e of 0 is 25. Okay, so he gave her a 25-foot head start. Okay, and you can tell by the distance between these two at time t equals 0 at the beginning. Does Max catch up to his sister? How can you tell? So when I look at this graph, okay, here's Max's travel and here's Evie's travel, and they only run for 20 seconds, it said back up in the problem. So does Max catch his sister? No. Okay. Because at 20 seconds, okay, Evie is at 60 feet. Is at 60 feet, and Max is at 50 feet. Okay. Now, next question says, how far does Max run during the 20-second race? Okay, so let's answer that question. So after 20 seconds, okay, Max has run 50 feet. So Max, after 20 seconds, he has run 50 feet. Okay. And then it says, how far does Evie run? So now let's be real careful here when we're looking about how far Evie ran. So you've got to keep in mind that Evie had a 25 foot head start. Okay? So it says Evie only runs 35 feet because she starts at 25 feet and ends at 60 feet. Okay, so her starting point was different. So after we've got at time 20, she is at 60 feet. Okay, so let's talk Evie. We see that she's at 60, but she had that 25-foot head start. So we got to subtract that away to say that she ran, okay, 35 feet. Okay, be real careful with that. Now it says, what calculation can you do to find Evie's distance? Okay, we subtracted. And part E says, how fast, okay, do both Evie and Max travel? So now we're talking about speed. In other words, how many feet do each of them run per second? Okay, so we're talking feet per second for each one of those. And then it says express your answers as decimals and make sure that you attach units. So we know for Max, he ran a total of 50 feet in how many seconds? 20 seconds. So there's our units, our feet per second. So now let's just do that division, and we end up with 2.5 feet per second. Okay, so every second he was covering 2.5 feet. Then what about Evie? Okay, Evie ran a total of 35 feet in 20 seconds. So again, there's our feet per second. Now just divide the 30 by 20, and we end up with 1.75 feet per second. Okay, so obviously who is running faster? Okay, Max is running faster, 2.5 feet per second, and she's 1.75 feet per second. Okay, all right, go ahead, flip the page. Now it says in the first exercise we are calculating the rate, okay, that the function's output, y values, were changing compared to the function's input, or x values. This is our average rate of change. So you might think you've seen this before, and you absolutely have. Finding the average rate of change is the same as finding the slope of a line. Okay, average rate of change for a line is the slope. There is, of course, a formula for finding that average rate of change, and it is right here. So it says, for the function y equals f of x, the average rate that f of x changes from some value of x, being a, to some value of x, being b, we would say f of b minus f of a. In other words, how much the y values change, the change in the y values, divided by b minus a, how much the x values change, the change in the x values. You may have seen this last year. I like to abbreviate and, use, sorry, just lost my cursor, change in y over the change in the x. I want to lose my cursor right now. That wouldn't be a good thing. Let's see if I can move this. Oh, good gravy. Okay, I'm going to leave it right there. So let me delve into what I just wrote a little bit. This little triangle is the Greek letter delta, and it means change. So the change in the y values divided by the change in the x values. That little triangle is the Greek letter delta. This is the same thing as this, which is the same thing as this. I tend to think that delta y over delta x is super fast to write and pretty quick to remember. By all means, use it. Okay? So it says, consider the given function given by f of x equals x squared plus 3. So we've got a quadratic because I've got something squared there, so that's a quadratic function. This isn't a line. Find its average rate of change from x equals -1 to x equals 3. It says carefully show your work that leads to your answer. So right now, I know my x values. So I'm going to write my formula down, my change in y over my change in x. I know the change in the x values. It's going to go from -1 to, if I can move, get that out of there. There we go. To 3. So -1, and keep in mind that change means we're subtracting, -3. So I know the change in the x. I've got to figure out the y's that go with those x's. Well, we can do that because we have the function. So if I need to find out the y that goes with an x of -1, I'm going to take that -1, my input, and put it into my function and get the output that goes with it. So this ends up being -1 squared plus 3, which is 4. So I've got the y that goes with an x of -1. Now I've got to find the y that goes with the other x, that 3. So I'm going to do the same thing. Got my function, now I'm going to put an input of 3 in. Well, what does this function give us? It takes and it squares the input and adds 3, so this is 9 plus 3, which is 12. Now I've got my other my other y value. And what does it say? That change, we've got to subtract minus the corresponding y value. So we end up with -8 over -4, which comes out to be 2. Okay? So my rate of change for this function is 2. Okay? We'll take a look at this later on, what this means graphically. Right now we're just kind of just calculating some numbers, finding that rate of change. Okay? We don't have what it looks like graphically right at the moment. Okay? All right. Now it says the function h of x is given in the table below. Okay, so we've got our inputs, our x's, and our h of x's, which is, in other words, our y's. Okay, which of the following gives the average rate of change over the interval, keep losing my cursor, over the interval from 2, which is less than or equal to x, which is less than or equal to 6. Show the calculations that lead to your answer. Okay, holy smokes. So what do we have here? So I'm going to write my formula down, change in y over my change in x. What do I have? What do I know? The problem gave us the x's from 2 to 6. So let's look at our table. Here's an x value of 2, and here's the x value of 6. So we know we're going to do 2 minus 6. Now, what are the y's that go with those x's? So what's the y that goes with the x of 2? Right there, 9. Minus, and what's the y that goes with the x of 6? And it's right there, 3. So we end up with 6 over -4, which then simplifies to -3 over, oh, don't move now, -3 over 2. Okay. I'm going to write this down here. Sorry about that. -3 over 2, or -3/2, which is choice 1. Okay. So now we've got another application problem, and it says Francis is selling glasses of lemonade. Here's our function, g of t is equal to t squared plus 4 divided by 2, models the number of glasses she has sold, g, after t hours. What is the average rate at which she is selling lemonade between 2 and 6 hours? Include proper units in your answer. Okay, so we've got our t values. So right now, it is glasses, okay? What are our units? Glasses per hour, right? So again, that average rate of change still stays our change in y over our change in x, or we could say, to think about the context to this problem, the change in glasses over the change in hour. Okay? So we know right now they gave us our time. Our t is 2 and our t is 6. So 2 minus 6. Now we've got to find the number of glasses that she sold in 2 hours. So that's where our function rule comes in handy. So let's find out what goes with that. So g of 2 is 2 squared plus 4 divided by 2. We end up with 8 divided by 2, which is 4. So at 2 hours, she sold 4 glasses. Minus, now let's find the t of 6. How many glasses did she sell in 6 hours? So g of 6, 6 squared plus 4 divided by 2, 36 plus 4, which is 40, divided by 2 is 20. So in 6 hours, she sold 20 glasses. So I want to know now what is her average rate at which she is selling lemonade between these 2 hours. So we end up with negative 16 over negative 4, which we know that that divides into 4. And now let's attach the units. Glasses per hour. Okay, 4 glasses per hour. All right, we'll continue to practice and have a good night.